Hello, good day. Today we will study on the topic interference of light waves. I am Dr. Subhendu Mondal. So this topic comes under the subject engineering physics. In this topic, we will describe only the wave property of light wave. But there was a debate between Huygens and Newton about the property of light. So Huygens proposed that light is of wave-like nature, it has wave-like nature, and Newton he proposed that the light is of kind of corpuscles. So this debate was overcome until after the experiment done by scientist Young, who showed that if you pass light wave through two slits, these light waves coming out from the two slits will form the interference. In the middle of 19th century, Maxwell showed that also light is of electromagnetic nature. And then in the middle of 20th century, Louis de Broglie discovered that light has both the wave-like nature as well as the particle-like nature. So which is known as wave-particle duality. But here we will concentrate only the wave-like nature, wave property of the light wave. So in this topic, we will discuss first about the interference effect, and then the types of interference effect, and then we will describe the double slit interference method, and then we will analyze the intensity of the double slit interference pattern, and from there we will obtain the condition for interference effect, and at the last we will describe about the Newton-Singh method for various applications. So what is interference? So you have seen all the waves. So you can see waves on the waterfront. So easily we can generate two waves on the waterfront just by throwing two stones using your two hands. So if you do that, the two waves at the 2 points will be generated, and if you observe what is happening at the point P, where the waves from A and waves from B will superimpose, we will have the maxima and maybe minima. So therefore, the phenomena of redistribution of light energy in the medium due to superposition of light waves from two coherent sources of light is called interference of light. Now, what are the various types of interference? So to know it, let's describe the two-slit method. Let's say you have two sources, source A and source B. So there may be chance that sometimes the wave coming from A and B, they are superposing at P due to waves from A and B. The crest due to one wave falls on the crest due to other wave, or in another case, trap due to one wave falls on the trap due to another B wave. So in this case, we will have a constructive interference. So here at this place, so as we are adding the amplitude of the same phase two waves, so we will have the amplitude will be maximum and we will get the maximum. At this place, the energy become maximum. On the other hand, if you have trap from one wave and crest from another wave superimposed, so we will have the positive amplitude and negative amplitude. After summation, they will nullify with each other and we will get the minima. So therefore, at this place, we will have the minimum energy, and such kind of interference is known as the destructive interference. Next, the classification of interference. So, in laboratory or in nature, the interference can be formed by division of wavefront method and division of amplitude method. In first case, we have which is division of wavefront. So you take one single wave and divide in many parts. So as we have discussed a slide before, that in case of double slit interference, you are dividing the wavefront in through two slits. So such kind of, therefore, the double slit interference method consists based on the division of wavefront method. And in some case, one light wave is taken and they split into two or more rays or waves by method of partial reflection or refraction. So this type of classification is known as division of amplitude. So here, such type of method is observed in neutron ring method. Now let's see what will be the interference intensity of the superposed waves when they will come out from the two sources and superimpose at a point of observation. Let's say, so here you see a monochromatic light is passed through a single source slit and a spherical wave will form, and from the same phasal point we will have the on a opaque medium you will have the two slits, and therefore the waves will be again generated. So we will have the two waves, they are generated from the S1 and S2 slits, and when these two waves coming out on the space, they will superimpose with each other. So what will be the interference? Mathematically we can calculate it. Let's say the wave y1 from S1 slit is A sin omega t, where A is the amplitude here in general we are taking, and y2 is B sin omega t plus phi. In general, let's say the phase difference between waves from S1 and S2 is phi. So after superposition, the resultant wave will be y is equal to y1 plus y2. So if you do that, we will have A sin omega t plus B sin omega t plus phi. So after rearrangement, we will get sin omega t multiplied by A plus B cos phi and plus cos omega t into B sin phi. So here, if you consider here the A plus B cos phi as R cos theta, where R is a constant term and theta is a constant phase angle. As well, R sin theta is equal to B sin phi. So we will get Y is equal to R sin omega t cos phi cos theta plus cos omega t R cos omega t sin theta. So we will get R is equal to Y is equal to R sin omega t plus theta. Now here R is the resultant amplitude after superposition. So to get the intensity, we will square the amplitude R here. So squaring this, we will get at the end A square plus B square plus 2AB cos phi. So here, depending on the value of phi, your intensity will change. So if for maximum intensity, when the value of phi is 0 plus minus 2 pi plus minus 4 pi, we will have intensity maximum that will be A plus B whole square. Okay? That means phi value here for maximum intensity is integer multiple of pi. And for minimum, when phi is plus minus pi plus minus 3 pi plus minus 5 pi, so we will have intensity minimum is equal to A minus B whole square, that is A minus B whole square. So for in case of A is equal to B, so the amplitude of the two waves, if they are same, then the minima should be 0, I mean should be 0, and in case of I max it will be 4 square. So we get the condition that for maximum intensity phi should be even multiple of pi, and for minimum intensity the phase difference between two sources will be odd multiple of pi. So therefore we can draw the conclusion that to observe the interference pattern, we will have the two sources of light must be coherent. Here we have taken both cases the frequency is omega same. So that's why it is monochromatic. So the sources must be preferably monochromatic, and amplitude must be preferably equal, because in that case we will increase the contrast. Because you see from the relation, if you have A is equal to B here, you will have the intensity maximum is equal to 4 square and intensity mean will be 0. So we will have the large difference between maximum and minimum intensity. So in this way we will have the contrast, maximum contrast. Now next we will move to the interference from a thin film. So here a thin film is produced if you place a planar convex lens on top of a glass plate. You will have the air between these two bodies. The air film is formed, and you see the thickness of the film gradually increase from point of contact to outward. Now, so in such type of arrangement, if light falls on it, you will have the light wave may be reflected from the lower surface of the planar convex lens, and another part may be transmitted and then may be reflected out from the glass plate, and it will go through the planiformis lens again. So when they will superimpose, these two waves will superimpose with each other, we will have the interference pattern. So therefore, for when monochromatic light is allowed to fall normally on the system, the pattern of alternative bright and dark concentric fringes with central dark is formed. Such kind of fringe formation in the shape happens in the shape of rings and was first started by Newton. That's why such kind of ring is known as Newton's ring. So here, as you see, the light is coming out after reflection. It may be possible that incident light, which is passing through the plano-convex lens and going down and falling on the glass plate. So it may be possible that ray may be transmitted to the glass plate, and another part is going out by reflection from the glass plate, and it may come back again to the glass plate by reflection on the surface of the plano-convex lens, and the second ray also may be transmitted to the glass plate. So we will have the two cases as well. So a pair of lights from the top of the plano-convex lens and a pair of light waves from the underneath the lens system. So we will have the interference if we see from the top of the lens and from the bottom of the lens system. So here we will concentrate only the light waves coming out by reflection. Okay, and this is the experimental structure, how we can observe the interference made by the Newton's ring arrangement in the laboratory. Here, monochromatic light comes from the sodium lamp and it meant to fall on a partially reflecting glass plate which is at 45 degrees. So therefore, a part of the ray will be falling, reflected down towards the lens setup. Okay, and after reflection, as we described, so the reflected will be go back. So therefore, we will have the interference pattern in the reflected rays, and that we can observe through the microscope. Here, as you saw, that ring, if you saw from the top of the lens setup, with the help of the microscope, we will have some kind of this bright and dark ring structure, where at the center we have the dark center. So to examine this, where we will have the maxima and minima, we consider, so we know that maxima and minima will happen where there is constructive interference, maxima will have occur, and where the destructive interference will occur, will have the minima. So therefore we have to know the phase at that point. So to get the phase at the point, we will have first obtain the path difference of the light waves coming out. So here we have, in case of wedge-shaped film, the path difference between the reflected ray is twice mu t cos r plus theta plus lambda by 2. We are coming to the next point. Here, mu is the refractive index of the thin film medium. So if you consider here the air as a thin film medium, so mu value is 1. And for normal incidence, r is equal to 0. And if you have the radius of curvature of the plano-convex lens is very large. So the theta, the contact angle will be 0, nearly equal to 0. So this reduced to the path difference is equal to 2 t plus lambda by 2. So this lambda by 2 comes, extra path difference comes following the Stokes law of reflection. So it happens when light ray get reflected in the denser media from the denser to, when light is going from denser to rarer medium. So extra phase is added, and that's why the lambda by 2 is added here, path difference. So to examine for bright ring formation, we have already learned that the path difference must be equal to even multiple of lambda by 2. So therefore it will be is equal to m lambda, and from there we get twice t is equal to twice m minus 1 multiplied by lambda by 2. In case of dark ring, so path difference must be odd multiple of lambda by 2. So therefore, by doing this, we get the condition that twice t. So t is the thickness of the film. Here t is the thickness of the film is equal to, considering here, so twice t is equal to m lambda for dark ring condition. And if you consider the geometry of the thin film, if you consider the geometry of the arrangement, so let's say we have a plano-convex lens, and this is a part of the sphere. So this is a plano-convex lens, and here it is center, and this is the radius of curvature is a capital R. And if T is the thickness of the film and R is the radius of the fringe, so here this quantity will be capital R minus T. So from the relation, we will have the capital R square is equal to small r square plus R minus T whole square. So here, from here we will get twice RT is equal to R square plus T square. And we can neglect the T square term, because if you have the capital R is very large, so the thickness of the plano-convex lens will be, or air film will be very less, so we can neglect the T square term. So therefore we will have twice RT is equal to small r square, and then twice T is equal to small r square by capital R, where capital R is the, remember, radius of curvature of the plano-convex lens, and small r is the radius of the fringe forming here. So therefore we'll have the relation for bright ring. We have that twice t is equal to r square by small r square by capital R is equal to twice m minus 1 into lambda by 2. So doing this, we get the diameter is equal to, diameter square is equal to 2 into 2n minus 1 into r lambda. And in case of dark ring, we have the relation that is twice t is equal to small r square by capital R is equal to m lambda, that we already obtained in the earlier slides. So this will give you the diameter square of the fringe is equal to 4mr capital R into lambda. So now using this, what we can do in the laboratory, we can determine the wavelength of unknown monochromatic light is by studying this neutralizing experiment, as well as we can determine the refractive index of a given liquid. So if you form instead of a thin film, instead of a air film, if you put liquid in between the plano-convex lens and a glass plate, so you will have we will form the film of that liquid, and we can easily determine the refractive index of the unknown liquid. So here is the theory that for the bright ring we have got this relation. The diameter of the mth ring is 2 into 2m minus 1 into r lambda. So if I take m plus pth ring, so in place of m you will add up, you will put m plus p, and then you will get the relation. And if you take the difference of the two diameters, you will have the relation, that is 4p r lambda. So p is the difference between the mth and m plus pth ring. So therefore, you can see readily that lambda you can obtain by dividing the difference by dividing 4 PR to the difference between the diameter square. You can easily, so in the experiment, what we can do, just to measure the m plus pth diameter and take the square, and measure the mth fringe diameter and take the square and take the difference. And if you divide this by 4PR, where R, capital R, is the radius of curvature of the plano-convex lens, you can accurately get the wavelength of the unknown monochromatic light. Similarly, we can determine the refractive index of a liquid. So if you put the liquid in between that plano-convex lens and the glass plate. So in case of path difference, we have done before. So we have taken earlier for air mu is equal to 1. So we will take mu here. So liquid will have some mu value. So then the path difference will be twice mu t plus lambda by 2. And for the bright ring, so diameter square will be that is 2 into 2m minus 1 into r lambda divided by mu here. Okay. In case of air film, so mu was 1, but here you will have the mu divided here. And for similarly for the m plus ph ring, you will take the diameter. And if you take the separation for two cases, so we will have for the liquid dm plus p square minus dm square. For liquid, it will be equal to 4p r lambda divided by mu. And in case of, then you do it for air, so only the mu will go out. And if you take the ratio between them, so differences of the diameter square for liquid by differences between the diameter squares of the fringe formed in air film, that will give you the refractive index value. So therefore, from this expression, we can easily determine the refractive index of the liquid. So there are various, instead of this simple two applications, we can use interference effect to explore or obtain various parameters. For example, you can measure the thickness of a thin sheet just by putting the sheet in the one path of the double slit experiment, and from there, by seeing the shapes, phase or thin shift, we can obtain the thickness of the narrow or thin sheet. Okay, so with this we finished quickly about what is the interference and the types of interference and the various applications, and So we will have we can formulate various numerical problems and the important questions that we may give in the description box. Thank you. Thank you all.